Primary concept number 4. Let V be an Euclidean space and alpha beta belongs to V. Now we have to show that inner product of alpha beta equals to 0 if and only if norm of alpha plus beta equals to norm of alpha minus beta. Now proof. Here alpha and beta belongs to V, alpha minus beta belongs to V. Therefore norm of alpha plus beta square equals to inner product of alpha plus beta comma alpha plus beta equals to inner product of alpha plus beta comma alpha plus inner product of alpha plus beta comma beta equals to inner product of alpha alpha plus inner product of beta alpha plus inner product of alpha beta plus inner product of beta beta equals to norm alpha square plus 2 inner product of alpha beta plus norm beta square. Also norm of alpha minus beta square equals to inner product of alpha minus beta comma alpha minus beta equals to inner product of alpha minus beta comma alpha plus inner product of alpha minus beta comma minus beta equals to inner product of alpha comma alpha minus inner product of beta comma alpha minus inner product of alpha comma beta plus inner product of beta comma beta equals to inner product of alpha comma alpha minus 2 inner product of alpha comma beta plus inner product of beta comma beta equals to norm alpha square minus 2 inner product of alpha comma beta plus norm beta square. Now let inner product of alpha beta equals to 0. Therefore norm alpha plus beta square equals to norm alpha square plus norm beta square plus norm beta square equals to norm alpha minus beta square. That imply norm alpha plus beta equals to norm alpha minus beta. Now conversely let norm alpha plus beta equals to norm alpha minus beta. Therefore norm alpha plus beta square equals to norm alpha minus beta square. That imply norm alpha square plus 2 inner product of alpha beta plus norm beta square equals to norm alpha square minus 2 inner product of alpha beta plus norm beta square. That imply 4 inner product of alpha beta equals to 0. That imply inner product of alpha beta equals to 0. Hence proved. Now the fifth concept. Let V be an Euclidean space and alpha beta belongs to V. Now we have to show that inner product of alpha beta equals to 0 if and only if norm alpha plus beta square equals to norm alpha square plus norm beta square. Now proof. Here alpha and beta both belongs to V. Therefore alpha plus beta also belongs in V. Therefore norm alpha plus beta square equals to inner product of alpha plus beta comma alpha plus beta. That is equals to inner product of alpha plus beta comma alpha plus inner product of alpha plus beta comma beta. That is equals to inner product of alpha alpha plus inner product of beta alpha plus inner product of alpha beta plus inner product of beta beta. That is equals to norm alpha square plus 2 inner product of alpha beta plus norm beta square. Now let inner product of alpha beta equals to 0. That imply norm of alpha plus beta square equals to norm alpha square plus 2 inner product of alpha beta plus norm beta square. That is equals to norm alpha square plus norm beta square. Conversely let norm alpha plus beta square equals to norm alpha square plus norm beta square. That imply norm alpha square plus 2 inner product of alpha beta plus norm beta square equals to norm alpha square plus norm beta square plus norm beta square. That imply 2 inner product of alpha beta 2 into inner product of alpha beta equals to 0. That imply inner product of alpha beta equals to 0. Concept so that a set of non-null orthogonal set of vectors is linearly independent in an Euclidean space V. Solution: let alpha 1 alpha 2 alpha n be an orthogonal set of non-null vectors in V. Be an orthogonal set of non-null vectors in V. Therefore alpha I not equals to theta for I equals to 1 2 n. That imply inner product of alpha I is greater than 0 for I equals to 1 2 n. Also inner product of alpha I alpha j equals to 0 for I not equals to j. Now let us consider C1 alpha 1 plus C2 alpha 2 plus Ci minus 1 alpha I minus 1 plus Ci alpha I plus Ci plus 1 alpha I plus 1 plus Cn alpha n equals to 0 for C1 C2 Cn belongs to real number. Now inner product of C1 alpha 1 plus C2 alpha 2 plus Ci alpha I plus Cn alpha n equals to inner product of theta alpha I equals to 0. That imply inner product of C1 alpha 1 alpha I plus C2 alpha 2 alpha I plus inner product of C3 alpha 3 alpha I plus Ci alpha I alpha I plus inner product of Cn alpha I alpha I equals to 0. That imply C1 into inner product of alpha I alpha 1 alpha I plus C2 into alpha 2 alpha I plus plus Ci inner product of alpha I alpha I plus Cn into inner product of alpha n alpha I equals to 0. That imply Ci into inner product of alpha I alpha I equals to 0. That imply Ci equals to 0 for I equals to 1, 2, 3 dot 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 n. Therefore, C1 equals to C2 equals to dot 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 Cn equals to 0. Hence, alpha 1, alpha 2 dot 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 alpha n is linearly independent.